Hello, in this video I show you some examples how to find partial derivatives. Okay, so first, what is a partial derivative? If you study function of one variable, you can use differentiation rules to find derivatives of this function, right? And we know that the derivative is the limit of f of x plus delta x minus f of x divided by delta x once delta x approaches 0. Everything is good. We define the derivative using limit, right? And we know from calculus 1 that the derivative is the instantaneous rate of change, right? Instantaneous rate of change. That is the velocity, right? And graphically, this is the slope of the tangent line, right? At some point, x in this case, yeah, at x, let's say that. All right, so when you study function of multiple variables, let's say function of two variables, z equal to f of x and y. So this function may describe some surface. Agree? Like you have three-dimensional space x, y, z in here. So, you know, the domain should be in the xy plane. Because, you know, this function depends on two variables, right? Each time when you want to find the value of z, you need to have two values, x and y. That means you have two coordinates of a point right here, x, y right here. And then you just plug x and y into the function, you get some value z. That is z equal to f of x and y. Make sense? So, you know, that's how we can look at this. Look at the function of two variables. And then when you change x and y, or x and y, you know, belongs to some region right here in the xy plane, you have some surface, right? You have some surface. That's the whole idea of function of two variables. Make sense? So now, what happens if you want to find the derivative of this function? So you need to find some direction. Is that correct? Because, you know, since you are in the plane, right here. At this point, you know, you want to find some kind of tangent line or, you know, or tangent plane, right? Let's say about tangent line or tangent plane to the surface at some point. So how to do that? That is the main topic of this video, right? You need to work with partial derivatives. Okay, so let's look at this. Suppose you have this surface, right? This surface. And you want to find the derivative in the x direction. What does it mean? That means you fix y, right? You fix y. You look at y as a constant, right? You look at y as a constant, so like right at this point, I can look at y as a constant. I write here y as a constant. So we fix y, that is the y. And in three-dimensional case, what is y equal to y0? That is the plane, right? And this plane is perpendicular to the axis OY, make sense? And intersect with the axis OY at y equal to y0, in case if this is 0, y0 in here. So we have some plane like this, make sense? And this plane will intersect with the surface by some curve, right? So you fix y0, and the plane y equal to 0 will intersect with the surface z equal to f of xy by some curve. Okay, and now you have a curve in the plane y equal to y0. You see that? Now you already have that. So the curve right here, actually that is space curve, right? But you might look at this as a plane curve. Make sense? That is space curve. That means the curve in the three-dimensional space. But at the same time, you can look at this as a plane curve. Why? Because this curve belongs to this plane. Make sense? And then in this plane, you can consider the tangent line to the curve at that point. So you have the point right here. You may consider the tangent line, right? The tangent line to this curve. And as we mentioned previously, the slope of that tangent line is the derivative with respect to the x. Is that correct? Because in this case, you already fixed y. So that is partial derivative of f with respect to the x. Similarly, you can consider partial derivative of this function with respect to the y when you fix x. Make sense? And then you have you fix x right here, and you have some plane which is perpendicular to the x-axis, and you consider the intersection between that plane with the surface. So you have another intersection, which is also a curve, you see? And then you consider tangent line, to that curve at this point. So you have partial derivative with respect to the y. Agree? So that is about your geometry of partial derivative. Or sometimes we say, yeah, derivative in the x direction or in the y direction. Make sense? All right, so let's look at this example. Z equal to x squared plus xy. I don't have any surface right here, but we know this function describes some surface in the space. Okay, I want to find partial derivative of this function with respect to the x and y. Okay, so let's find z with respect to the x. As we discussed previously, when you differentiate with respect to the x, your y is a constant. Means y can be considered as a constant. Makes sense? Because we already fixed that plane right here. So I just differentiate this function with respect to the x. Makes sense? So in here I have x squared prime plus xy prime. X squared prime with respect to the x is 2x. And derivative of xy with respect to the x is just y. Agree? Because y is constant, so you can take that out. And the derivative of x is just 1. That's it. Similarly, you can find the derivative of z with respect to the y. So you write derivative of this and then xy derivative. What is the derivative of x squared with respect to the y? That is just 0. Because x squared is a constant in this case. Makes sense? And for this, you get x. You see? It's not that, difficult. Makes sense? If you have function of more than 2 variables, no problem. Let's consider that. Like you have function z, x, y, and z equal to ln of x squared plus y squared minus z squared, okay? And then plus x squared y z cubed. Let's say that. Now we need to find partial derivative of this function with respect to the x, y, and z, okay? So I have g with respect to the x equal to, I differentiate this function with respect to the x and look at y and z as constants. So basically, you might think, yeah, that looks like ln of x squared plus c. Don't forget that. And the derivative of this guy with respect to the x will be u prime over u, right? Because the chain rule says ln of u is u prime over u. So u prime is x squared plus c. The derivative of x squared plus c with respect to the x is just 2x. In here I have u is x squared plus y squared minus z squared. So that is the derivative of the first term, okay? This is not very correct, but you know that what we are doing here is just the derivative of the first term. And now we need to find the derivative of the second term. So let's do that separately. Again, I look at y, z cubed as constant. So this function is nothing but, you know, like cx squared. Makes sense? And the derivative of this will be 2cx squared, which is 2yz cubed x squared. Overall, I will have the following one. Gx equal to 2x over x squared plus y squared minus z squared plus 2x squared yz cubed. Similarly, we can find gy. I have 2y in here divided by x squared plus y squared minus z squared. And I differentiate the second term with respect to the y. I have x squared z cubed. And then g with respect to the z equal to negative 2z, because here we have minus z squared. Makes sense? And then divide by x squared plus y squared minus z squared. And we differentiate the term, the second term with respect to the z. I have plus 3x squared y z cubed, z squared. I think I did some mistakes right here when I calculate the derivative with respect to the x. So I think that should be, oh, it's very, very interesting. That should be without square, okay, and here without square. So please fix that. I don't have square in here. Make sense? That's it. Now let's talk about Jacobian matrix. Suppose that you have some function z equal to f of x and y, and x and y are functions of, let's say, t1 and t2. You know, we might consider more general case when, you know, function is more than, we may consider more general case when the function depends on more than two variables and x and y are functions of more than two variables too. Make sense? Now you want to change. You don't want to work with x, y. You want to work with t1, t2, right? So basically, if you want to do that, you have f equal to z equal to f of x t1, t2, and y t1, t2. And your function z right now depends on t1, t2. Make sense? And, you know, in reality, when you do integration and when you do whatever with the function z, and you involve changing variables in here, you need to find partial derivatives of x with respect to t1 and t2, and then you have to set up such called Jacobian matrix. Okay, so how can we define the Jacobian matrix? We have the following one. I have j equal to partial derivative of x with respect to t1 and partial derivative of x with respect to t2. In the second row, we have partial derivative of y with respect to t1 and here we have partial derivative of y with respect to t2. That's how we can determine the Jacobian matrix. Make sense? All right, so you have function z depending on x and y. At the same time, x and y are two functions of t1 and t2. Okay, you can define Jacobian matrix like this. You take partial derivative of x with respect to t1 and t2, and you write them in the row form. You have the first row. Similarly, you can find partial derivative of y with respect to t1 and t2. You have the second row of this Jacobian matrix. Of course, you may generalize this, right? Let's say you have function z equal to f of x1, x2, xn, and x1, x2, xn are function of, let's say, t1, t2, and tm, right? So the function z has n variables, and each variable is function of t1, t2, and tm. So in that case, I have Jacobian matrix. So you would guess, yeah, we have n variables in here. So we have n rows, right? And then we have m variables, t1, t2, tm. So we have n columns. Makes sense? In the first row, you have partial derivative of x1 with respect to t1, partial derivative of x1 with respect to t2, and so on. You have partial derivative of x1 with respect to tn. And so you move to the second row, you do almost the same thing. With x2, you have partial derivative of x2 with respect to t1, x2 with respect to t2, and so on. Partial derivative of x2 with respect to tm, and so on. The last row would be partial derivative of xn with respect to t1, partial derivative of xn, with respect to t2, and so on, partial derivative of xn with respect to tm. So basically, this matrix has the size n by m, where n is the number of variables x1, x2, xn, and m is the number of variables of function x1, x2, xn, which is t1, t2, tm. All right, let's consider the following example. So you have two functions, a1, which is pi L1 square over 8 plus L1 L3 over 2 plus L3 L2 over 2. The second one is A2 is L1 L3 over 2 plus L2 L3 over 2. Actually, I picked this example from the textbook for geometric majors, and this is called partitioner tract of land. Okay, and they ask you to evaluate the Jacobian matrix G. Okay, so in this example, very specific example, it says Jacobian matrix is formed by considering that there are three measurements L1, L2, L3 involved in the two equations representing the two areas A1, A2. So basically, A1, A2 are areas, right? And you would think, yeah, A1 and A2 is a pair of areas, right? And this plays the role of X, and this guy plays the roles of Y, right? Or X1 and X2. And right now, X and Y depends on L1, L2, and L3. Agree? So you would think, yeah, we can make the Jacobian matrix, and the Jacobian matrix has the size 2 by 3 because, look at this. I have said 2 by 3 right here. 2 is the number of variables, x1, x2, in this case, y and x. And 3 are L1, L2, and L3. Okay, so we just need to find partial derivatives, right? So I have j equal to, in the first column, I need to find partial derivative of a1 with respect to L1, L2, and L3. Look at this. Here's a1. I can find right here and I just copy, okay? So I have partial derivative a1 with respect to L1. I look at L2 and L3 as constants. So I will have pi 2L1 over 8 and then L3 over 2, and the derivative of the last term is just 0 because it does not have L1, right? Overall, I can simplify. I get pi L1 over 4 plus L3 over 2. All right, so secondly, I have A2 dL2, which is just L3 over 2, because in the first two terms, we don't have L2, right? And we have here should be A1 with respect to L3, which is L1 over 2 and plus L2 over 2. So I just copy these three values and write them in the row form. I have the first row of the Jacobian matrix. So in here, I would have pi over 4 L1 plus L3 over 2, and then L3 over 2, and then L1 over 2 plus L2 over 2. That is the first row. You see that? Similarly, you can find the second row. So you need to find partial derivative of the function A2 with respect to L1 and L2 and L3. So I write it in short in here. With respect to L1, I have L3 over 2. With respect to L2, I have L3 over 2. And with respect to L3, I have L1 over 2 plus L2 over 2. So this is our Jacobian matrix. Make sense? In case, if they give you the value L1 equal to 50 meters, for example, L2 is 20 meters or miles, whatever you want, and L3 is 30. Okay, so you just plug everything into this to find Jacobian matrix. Makes sense? All right, so let's do this. And at this moment, you can plug L1, L2, and L3 into J to find Jacobian matrix. So I write J at 50, 20, and 30 is equal to matrix. I can plug, into this. I have the following numbers: 54.3, 15, 35, and then 15, 15, and 35. Okay, so that is the Jacobian at this point. Let's say L1, L2, and L3. All right, so I have a homework for you. We have function w equal to xy plus yz plus xz, where x is s cos psi of t, y is s psi of t, and z is t. Please find the partial derivatives of w with respect to the x and y and z, and find the Jacobian matrix at the point s equal to 1 and t equal to 2 pi. All right, thank you.